Welcome viewers. In this video we will see the construction of three-phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic, construction of three-phase induction motor. This induction motor consists of two main parts are available. The first one is the stationary part called a stator. Stator is a stationary part in which the three-phase winding is placed. Stator is a stationary part in that stator windings are available. The rotating part is called a rotor, which is connected to the mechanical load through the shaft. The load is connected through the rotor. This rotor also having the winding or copper bars. So mainly we have the two parts, stationary part stator and rotating part rotor. Now we will see the diagram. So this is the overview of the three-phase induction motor. So this is the outer part is the stator. This portion is nothing but a stator slot. The windings are placed in the places. These slots are provided for placing the winding, stator winding. So this inner part is the rotor, rotating part, through which the load is connected. This is the shaft. This rotor is placed in the shaft. So here also the slots available, the copper winding or copper bars are placed in the rotor. So the stationary part stator having the stator winding, the rotating part rotor that also having the copper winding or copper bar. This rotor is placed in the shaft. The load is connected to the load through the shaft. Now we will see the description. It has laminated construction made of stamping which is 0.4 to 0.5 millimeter thickness. It's a laminated. This iron core is highly laminated in order to avoid the eddy current loss. So it is not a single piece. The n number of thin sheets are combined together, laminated and combined together with a thickness of 0.4 to 0.5 millimeter thickness. The stamping have the slot on the inner periphery to place the stator winding. So this is nothing but this is the core, laminated core. The slots are available. In that slot only the stator winding is placed. The stamping is made up of silicon steel. So it's made up of a silicon steel that is fully laminated. The number of stampings are stamped together to form the stator. Like a paper, n number of stampings available. All these stampings are laminated and compressed, pressed together to form the stator. It's not a single piece. N number of thin sheets available that are combined together to form the stator. Laminated silicon steel stamping minimize the eddy current loss. So why we are going for lamination and why we are going for stamping means in order to reduce the eddy current loss. The stator core consists of three-phase winding connected in either star or delta are called a stator winding. So the stator core having the winding connected in either in star connection or delta connection, that is called a stator winding. The stator winding is excited by the three-phase supply to produce the rotating magnetic field. So the stator winding is connected to the three-phase supply. So it will produce the rotating magnetic field. Rotor is placed inside the stator. Just now we discussed the diagram. The rotor is available inside. So it is laminated and slots on the outer periphery to carry the rotor winding or rotor conductors. So this rotor also having the slots that are also laminated and also having the slot. In that slot the rotor winding or rotor conductors are placed. So it is made up of a cast iron. There are two types of rotor construction available. The rotor, there are two types. One is the screw gauge rotor, another one slip ring induction motor or phase wound rotor. So this screw gauge means the copper bars are available. Slip ring means the separate winding is available. That is a major difference. So this one can be modified. This windings are this is permanent. The copper bars are permanently placed in the rotor. So that there are majorly two types, screw gauge rotor slip ring induction motor or phase wound rotor. First we will see the squirrel gauge rotor. So this is a rotor. So this is nothing but a copper bar. These lines are nothing but copper bar. Copper bars are permanently placed. So that will act as a copper winding or act as a rotor winding or rotor conductor. So we cannot modify. During the construction itself, the copper bars are permanently placed. But in case of slip ring, we can add some external resistance. We can modify the winding also. But this is permanently placed. So there is no modification can be done in this type squirrel gauge rotor. Now we'll see the construction. It consists of cylindrical laminated core. So this is cylindrical. It's like a cylindrical laminated core with slots to place the rotor conductor, which are nearly parallel to the shaft axis or skewed. Skewed means slightly it is having the inclination. It's not a straight line, inclined. Right. So there are lot of advantage available to place the rotor conductors in a skewed manner. Right. So here it is the laminated core, slots are available in the rotor conductors are placed in a skewed manner. The rotor conductors are not wires, but the bar of copper or aluminum or alloy. This is not a wire. The copper bars are permanently placed in the slots. One bar is placed in each slot. Each slot having one bar. At the end of the rotor bar conductors and short circuited by heavy end rings. So all the copper bars are short circuited by using the end ring. Since the rotor bars are permanently short circuited, it is not possible to add external resistance. So I already told in the second type we can add the external resistance. In first type the copper bars are permanently placed. So not possible to modify the resistance, not possible to add any resistance. In series with the rotor for starting purpose. During the starting, if you add the resistor, the motor will take the less current. We can reduce the starting current, but that is not possible in case of this squirrel gauge rotor. So the rotor is skewed because we already told it's not a straight line, it is a skewed because there are two different purposes available. It helps the motor to run quickly with reduced noise. The noise is reduced. Reduces locking tendency of rotor. The locking between stator and rotor is reduced because of skewed. If it is placed in a straight line or normal line, there may be a possibility of locking. If this skewed means there is some phase difference will happen between stator and rotor. So that reducing the locking tendency, that is rotor teeth remains under the stator teeth due to the magnetic attraction between the two. There is we can avoid the locking of between the stator and rotor. Now we'll go to the second type, slip ring rotor or phase wound rotor. So in the slip ring rotor or phase wound rotor, separate windings are available for the rotor. So this is the stator. Consider this is the stator. 3-phase supply is given to the stator. So we have the rotor available here. Rotor is available. That also it is connected in a star connected. So that is connected to the slip ring. So these are the windings. The brushes are available. Through the brushes the supply is given to the rotor windings. Right. So this is shaft. Shaft is available. So this shaded portion is the brush. This portion is nothing but a slip ring. Right. So the windings are placed in a rotor. In a previous case, the copper bar or aluminum or alloy bar available permanently. But here the windings are placed. The supply to the winding is given through the slip ring and brushes. So the other end we can easily add the resistor. So this is the external resistance. Right. So it is in a maximum resistance position. The resistance is maximum, so that current taken by the motor is very lesser. Thereafter we can slowly reduce the resistor so that the current increases gradually, so that voltage and speed also increases gradually. So it is possible to add the external resistance in this type, slip ring rotor or phase wound rotor. This external resistor are used to limit the starting current. That is the main purpose. So this facility available in the slip ring or phase wound rotor, that is not possible in the squirrel gauge rotor. Now we'll see the description. So it is in this rotor winding is similar to the stator. Stator and rotor windings are similar. Rotor carries three-phase star or delta connected winding. Either star connected or delta connected windings are available. These windings are placed in slot in rotor, is placed in the slot. One end of all windings are connected to the common place. The other end of three-phase windings are brought out and connected to the slip ring mounted on the shaft with the brush on them. So one end is connected commonly, another end is connected through the slip ring and brushes. So that is available here. So this is a three-phase winding, star connected winding. In this diagram, star connected windings are available. So the one end is connected commonly. One end of all three phases are connected. So this is the common point. The other end is connected to through the brush and slip ring. Okay, that is given here. One end is connected commonly, another end is connected through the brush and the slip ring. These brushes are then externally connected to the three-phase star connected rheostat. The external resistance are connected, and other end is connected through the rheostat. Why we are connecting this rheostat? The use of brush, slip ring and external resistor is to increase the starting torque and decrease the starting current. While adding the resistance, we can increase the torque, because initially the starting torque will be more, right? This purely depends upon the resistance value. When the resistance is more, the torque also more, and reduce the starting current. So by slowly decreasing the resistor value, we can slowly increase the voltage applied and current taken, so that it is possible to go for a speed control of the motor, right? Initially the resistor is in the maximum resistance position, so the current taken is very lesser. By slowly reducing the resistance, we can increase the current applied to the current taken by the motor, voltage applied to the motor, so that we can control the speed of the motor. Now we will compare this screw gauge rotor and slip ring or phase wound rotor. The comparison we will see the comparison. So here we will see the screw gauge rotor and slip ring or phase wound rotor. So in the screw gauge rotor, the rotor consists of bar of copper bars available, but here three-phase winding is available. In slip ring we have three-phase winding. The construction is simple. During the construction itself, the copper bars are placed. There is no more alteration. But here construction is complicated, because we need to place the three-phase winding. So because of this copper bar, the resistance cannot be added. But here we can add the resistor. Externally we can add the resistor. So there is no slip ring and brush. But here, because of three-phase winding, in order to get the supply, we need a slip ring and brushes are available. Right. So due to this, the rotor is cheap. During the construction itself, the copper bars are placed. So it is cheap, but here it is costly, because we need to place the winding. The moderate starting torque here, but here high starting torque. Why? Initially we added the resistor, so the torque is proportional to resistance value. Initially the resistor is very high, so that we get the high starting torque. So due to this starting torque and external resistors available here, but is not available here, speed control is not possible by adding the external rheostat, since the rotor is short circuited. The main advantage is here is we can go for a speed control by adding the external rheostat is possible. That is not possible in the screw gauge rotor. Rotor copper loss is less, and so that high efficiency. So because here there is no copper winding, copper bars only available. So automatically the loss due to the copper is lesser, so that we can get the more efficiency. But this rotor's copper loss is more, because the copper winding is available. Here copper bars are available. So we will get the less efficiency compared to the screw gauge rotor. So it is mainly used in the lathe, drilling, fan, blower, water pump, grinder and printing machines, where we need the moderate torque is required. This one having high starting torque, so used in the lift and hoist. So these two are, and crane, this and elevator, compressor, these are all started with the loaded condition. So we need definitely we need the high starting torque. Lift means already the passengers are available. So lift hoist means the load is available. So for that case we are using this slip ring slip ring or phase wound rotor having the high starting torque. So in this video we discuss about the construction of three phase induction motor, stator and rotor. Main part is stator and rotor. The rotor again having two types, squirrel cage rotor and slip ring rotor. The construction we discuss, and also we discuss the comparison between squirrel cage and slip ring rotor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Viewers, in this video we will see the principle of operation three phase induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic, three phase induction motor working principle. It works on the principle of electromagnetic induction. When a three phase supply is given to the three phase stator winding, rotating magnetic flux RMF is produced. So it is based on the electromagnetic induction. The rotating magnetic field is produced in the stator while giving the supply. Now we will refer the diagram. So this is the stator available. This is the rotor conductors. So initially we are giving the supply to the stator winding. So due to that, the rotating magnetic flux, the fluxes keep on changing because of three phase AC supply. The voltage level keep on changes. So the flux produced in the stator due to the three phase winding, that also keep on changing. That is called a rotating magnetic flux. Initially these rotor conductors are in a stationary position. It's not rotating, stationary position. So this magnetic flux is linked with the stationary conductors. So what will happen when a conductor cuts the magnetic flux and EMF is induced, right? Based on the principle, this magnetic flux cut the conductors. Initially this conductor is a stationary, there no current is flowing in the rotor conductors. This magnetic flux will cut these conductors. So when a conductor cuts the magnetic flux, what will happen? The EMF is induced in the rotor conductors. These rotor conductors are in a closed circuit, so the current will start flowing through the rotor conductors. So refer this diagram. So this dotted line is indicate the direction of current in the rotor. Initially there is no current. So after the interaction with the magnetic flux, EMF is produced. This EMF will circulate the current in the rotor because of closed circuit, that is indicated in this diagram. Now what will happen? This rotor conductor become a current carrying conductor. Initially stationary conductors, because of interaction of the flux, the current is flowing. So it is a current carrying conductor. When a current carrying conductor placed in a magnetic field, due to the law of interaction, when a current carrying conductor placed in the magnetic, what will happen? It experiences a force. So that is given in the third diagram. So this is the flux direction. This is the direction of the force, right? When a current carrying conductor placed in the magnetic field, it experiences a force. So all conductors are connected together. So the force by the all conductor will tends to rotate the rotor. The rotor starts rotating, right? So this is the basic principle of the induction motor. Initially the supply is given to the stator, so the rotating magnetic flux is produced. This flux cut the rotor conductors. Due to that, EMF is produced. That EMF will circulate the current. Now the current carrying conductor placed in the magnetic field, due to this it will experience a force, so it will start rotates, right? So this is the basic principle. Now we'll see the description. We'll see what is the speed of the rotor and other things. The speed of the rotating magnetic field is synchronous speed, ns, right? The speed of the stator is the nothing but synchronous speed. How will calculate the synchronous speed? Ns equal to 120 f by p. All are constant. Frequency is constant and number of pole is constant. So from that we can find the synchronous speed. Synchronous speed means the speed at which the motor is designed, right? It is based on the supply frequency and number of poles. Let the direction of rotating magnetic field is in clockwise direction. We'll consider clockwise direction, right? Now the rotor is stationary. Stator magnetic field is revolving at a speed of ns. This revolving field cut the stationary rotor conductors. When a conductor cuts the magnetic flux, an EMF is induced in the conductor. When there is a closed path, current start flowing to the EMF, right? So initially the rotor is stationary. This rotor conductor cut the magnetic flux, so that EMF is induced. That EMF will circulate the current because of closed circuit. Now what will happen? Now we have current carrying conductor placed in the magnetic field. By law of interaction, when a current carrying conductor placed in a magnetic field, the conductor experiences a force. Hence all the conductor experience a force which together give a torque which tends to rotate the rotor. So due to the experiencing the force, all the conductors are having the together connected together, so it will start to rotate with the required torque. The direction of force is same as that of rotating magnetic field. Hence the rotor start rotating in the same direction as the magnetic field. The rotation of the rotor and rotation of the rotating magnetic field in the stator both are in same direction. Now we'll see the speed of the rotor as well as the speed of the stator. This is a very important thing. Ns is the speed of rotating magnetic field in RPM. That is the speed of the rotating magnetic field. But N is the speed of the rotor. This is the actual speed of the motor. This is the speed at which the motor is designed. This N is the speed of the rotor or actual speed of the motor. The difference ns minus n is nothing but relative speed between the two, between the stator and rotor, ns minus n. The rotor always rotate in the same direction as that of rotating magnetic field, right? Ns minus n is the relative speed. Now we'll see analyze that what will happen if ns equal to n. Ns is the synchronous speed and n is the actual speed. If both are equal, whether it is possible to have the synchronous speed and speed of the rotor. When the rotor rotates it, try to catch the speed of the rotating magnetic field. The rotor will try to catch. If it is catches the speed of rotating magnetic field, then the relative motion of the is 0. That is ns minus n. Both are equal means it becomes 0. Therefore, the relative motion in the main cause for EMF is also 0. Because if both are equal mean, both of equal speed mean the relative speed is 0. So the relative motion, that is the important cause for EMF, is also 0. So the rotor flux required to produce torque is also 0. Therefore the rotor will not rotate. If both are equal, what will happen? The relative speed becomes 0, EMF becomes 0, so the torque produced also 0, the motor will not rotate. So the induction motor never runs at the synchronous speed. That is the important thing. The induction motor never runs at the synchronous speed. The speed at which the motor rotates is called a subsynchronous speed. It is always subsynchronous speed. Or otherwise, it is due to that it is called a asynchronous motor. We have synchronous motor available, always rotating in the synchronous speed. But this induction motor never run at the synchronous speed. So that is called a asynchronous motor. If it is rotated at synchronous speed, what will happen? The rotor will not rotate due to the relative motion is 0. So in this video, we discuss about the working principle of three-phase induction motor based on the rotating magnetic field of the stator, then the rotation of the rotor. If both are equal, what will happen? That also discussed. Finally, we see that it is a asynchronous motor. Subscribe this channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the slip of induction motor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic, slip of induction motor. Now we'll see the speed of the stator. is nothing but a speed of rotating magnetic field or synchronous speed equal to ns. This ns is nothing but synchronous speed. The motor designed at the time of designing, the speed is the ns. Also it is called a speed of the stator or speed of the rotating magnetic field. But the actual speed of the motor or rotor, speed of the rotor is n. The difference between these two, n and ns, is nothing but a slip of the induction motor. So the slip is measure of difference between the synchronous speed and its shaft speed. The difference between these two is nothing but a slip of induction motor. So based on that we can calculate the slip speed. ns minus n is nothing but a slip speed. The speed slipped is nothing but difference between synchronous speed and the speed of the rotor. So that is the difference between the speed of the rotating magnetic field and that of rotor is called a slip speed. Now we will see the definition of the slip. The slip is also called as a absolute slip or fractional slip. The another name is absolute slip or fractional slip. So that is the difference between the synchronous speed and actual speed of the rotor, ns and n, expressed as a fraction of synchronous speed is called a slip of the motor. That is ns minus n divided by ns. Right? The difference between synchronous speed and speed of the rotor expressed in terms of synchronous speed ns is nothing but a slip of the induction motor. While taking percentage of slip, ns minus n divided by ns into 100. We need to multiply with 100. Now we will see the speed of the motor in terms of the slip. The speed expressed in terms of slip. We know that s equal to ns minus n divided by ns. So cross multiply this. So s into ns equal to ns minus n. Right? Bring this n in the left hand side, s ns in the right hand side. So while coming this side, this minus n become plus n. This s into ns become minus s into ns. The ns available commonly, take ns outside, so that n equal to ns into 1 minus s. So the speed of the motor in terms of synchronous speed and slip is n equal to ns into 1 minus s. Now we will see the slip at the various stages, starting and running condition. Slip at the starting condition. We will see what is the slip at the starting condition. So at the time of start, the speed of the motor is 0. So at the beginning, it is that there is no speed, so n equal to 0. The definition of slip is s equal to ns minus n divided by ns. Now the n is 0. N is 0, so it becomes ns by n. So that is equal to 1. So s equal to 1. So at the beginning, at the starting condition, the slip of the induction motor is 1. So this is the maximum value of the slip, and that is occurred at the starting condition. So this s equal to 1 is the maximum value that will occur in the starting condition. When s equal to 0, what will happen? When s equal to 0, ns equal to n, because we know the formula n equal to ns into 1 minus s. If s equal to 0 means 1 minus 0 is 1, so n equal to ns. Synchronous speed and speed of the rotor both are equal, but ns equal to n is not possible for induction motor. So that slip of the motor cannot be 0 at any case, right? So this ns minus n is not possible. If synchronous speed and rotor speed is equal, then the rotor will be locked. The rotor will not rotate, right? So the slip cannot be a 0 value, right? So at the any case, the slip is not 0. So it is greater than 0, and also it is maximum of s equal to 1. The minimum value is greater than 0, maximum value is 1. Now we will see the effect of the slip on the rotor parameters. Various rotor parameters, what will happen due to the slip. Let us study the effect of slip on the following rotor parameters. We are going to study the 5 parameters. Due to the slip, what is the effect of the slip on rotor frequency, magnitude of rotor induced EMF, rotor reactance, power factor, rotor power factor, and rotor current. We are going to analyze the effect of the slip based on these 5 parameters of the rotor. First we will see the slip of the frequency, effect of slip of on frequency of the rotor current. Right. So when the rotor is stationary, the frequency of the rotor current equal to supply frequency. Both are equal. At the stationary condition, the supply frequency and rotor current frequency are equal. When rotor is rotating, the frequency of the rotor current will depends upon the slip of the speed, slip speed. So when the motor rotates, the speed decreases. So the frequency of the rotor current depends upon the slip speed. That is called as Fr. We will take Fr. F is the supply frequency. Fr is the frequency of the rotor under running condition. Frequency of rotor current at running condition. Now we will analyze this. So we know that the synchronous speed ns equal to 120 f by p, standard formula is available, right. So ns minus n, the difference between the synchronous speed and rotor speed equal to 120 fr by f, fr by p, the rotor. This is the frequency of the supply, this is the frequency of the rotor current. So at that time there is a difference in the speed, ns minus n, difference between ns, the synchronous speed and normal speed. Now from these two equation, we will go for this take this is equation 1 and equation 2. We will go for equation 2 divided by equation 1, ns minus n divided by ns, right. So the ns minus n is 120 fr by p, this ns is nothing but 120 f by p, right. This is rotor current frequency, this supply frequency. 120 got cancelled, this p also got cancelled. So what we got, ns minus n divided by ns equal to Fr divided by F, rotor current frequency divided by supply frequency. So we know that ns minus n by ns is nothing but a slip of the induction motor, S, right. So that S equal to Fr into F, right. Bring this F in this side, so that Fr equal to S into F. So the frequency of the rotor current is nothing but slip into supply frequency, right. So during the starting condition both are equal, supply frequency and rotor frequency is equal. During running condition it is depends upon the slip of the induction motor, so that Fr equal to S into F, frequency of rotor current, Fr equal to S into F. Now we will see the induced EMF, effect of slip on rotor induced EMF. Again we will start with the stationary. When the rotor is stationary, S equal to 1. So at stationary condition, relative speed is maximum, EMF induced is maximum, and the proportional synchronous speed is also proportional to ns. E2 is directly proportional to ns. E2 is nothing but EMF induced in the rotor when it is stationary, right. So during stationary condition, S equal to 1, speed is maximum, induced EMF also maximum, that is depends upon the synchronous speed. E2 is directly proportional to N2, right. E2 is nothing but EMF induced in the rotor during the stationary condition. So at the running condition what will happen, as rotor start rotating, relative speed between the rotating magnetic field and rotor decreases, and hence EMF also decreases, and it is proportional to the relative speed ns minus n. So at the beginning it is both are equal, so it is proportional to ns. When it is start rotating, there is a difference between the relative speed and speed of the rotor, so the induced EMF is depends upon ns minus n. So that E2R is directly proportional to ns minus n. E2 means rotor EMF induced in the rotor under starting condition. E2R refers EMF induced in the rotor under the running condition, that is depends upon difference in the speed, right. So that is given, rotor induced EMF at the running condition, right. Now we will go for the ratio E2R divided by E2. E2R is ns minus n, E2 is ns. We are going to divide the two equations, above two equations, right. So this ns minus n by ns is nothing but a slip of the induction motor, yes, we know that. So that E2R divided by E2 equal to S. So cross multiply this, so E2R equal to S into E2. So the rotor induced EMF under running condition is depends upon the slip of the induction motor, right. Thus during starting condition both are equal, E2R is directly proportional to N2. Now it is depends upon the slip of the induction motor. Now we will see the effect of slip on rotor resistance and reactance R and X. So the rotor winding has its own value of resistance and reactance. Now again we will start with the starting condition. At the starting condition, standstill condition, N equal to 0. We will take this R2 is rotor resistance per phase. X2 is the rotor reactance per phase. Right. So at the standstill, FR equal to F. Both are equal. Supply frequency and rotor current frequency both are equal. Right. So if L2 is the impedance of the rotor, so we can write X2 equal to 2 pi F into L2 ohm per phase. So general formula, reactance X equal to 2 pi FL. So in that we are taking L2 is the impedance of the rotor, right? L1 refers stator, L2 refers the rotor, right? So under starting condition N is 0, so the reactance is X2 equal to 2 pi FL2. This R2 as it is, we can take as it is. Now we will go for a running condition. So under the running condition, FR equal to S into F, that we already discussed. The frequency of the rotor under running condition is slip into F. So X2R equal to 2 pi FR into L2. So this is X2 is the reactance under standstill condition. X2R means under running condition. So that is F2 pi. This F also now replaced by FR under running condition into L2. But this FR is nothing but S into F. So 2 pi FR is replaced by S into F L2. So that is nothing but S into 2 pi FL2. This 2 pi FL2 is nothing but the X2. So S into X2. So the reactance of the rotor under running condition is depends upon the slip of the induction motor, S into X2, right? So this X2R is the rotor reactance at running condition. Rotor reactance is same at standstill and at running condition. The resistance value is same. It is not depends upon the slip. Resistance value is same for both standstill as well as running condition. Now we will go to the impedance. So the rotor impedance at standstill is very simple. Z2 equal to R2 plus JX2. Resistance and reactance. So while taking magnitude, it is square root of R2 square plus X2 square under the standstill condition. But in case of running condition, Z2R, Z2 refers starting condition, Z2R means under running condition. So that R2 plus JX2R, R2 is same for standstill as well as running condition, but the impedance, but the reactance will be X2R. It become X2R. This is a starting condition, this is running condition. So while taking magnitude, it is square root of R2 square plus X2R square. X2R is nothing but S into X2. Just now we discussed. So replace this X2R by SX2. So this is the impedance under the running condition. So this depends upon the slip of the induction motor. Now we will see the rotor current, effect of slip on the rotor current. Let us take I2 is the rotor current per phase at standstill. I1 refers the stator current. I2 means is a rotor current. E2 EMF per phase at standstill. Z2 impedance per phase at standstill. Right? We already discussed E2 and Z2. Right? So that we will go for I2. I2 is E2 divided by Z2. So that E2 divided by square root of R2 square into plus X2 square. Right? This is for under the standstill condition. Somehow same thing will go for a running condition. I2R. I2 means starting condition. I2R refers rotor current per phase at running condition. Similarly, E2R is nothing but S into E2, that already we discussed. Right? So the EMF per phase at running condition. So that Z2R equal to R2 square plus S into X2. Previously we have only X2. Now it is S into X2, right? So these two things are we already discussed, the details about I2 and E2. Now we got the impedance. From that we can easily calculate the rotor current. I2R equal to E2R divided by Z2R. right? So the E2R is S into E2. Z2R is now just now we calculated square root of R2 square plus X into X to the whole square. So this rotor current under the running condition is depends upon slip of the induction motor. Now we'll go to the power factor, effect of slip on the power factor. Now consider this impedance triangle, the angle pi 2 is there, the resistance is a reference. In this with the 90 degree we have the reactance. The vector sum of these two is the impedance. So general impedance diagram, resistance, reactance and impedance. So at the standstill condition, this cos pi 2, this cos pi is nothing but a power factor. So cos pi 2 means this is opposite side, this is adjacent side, this is hypotenuse. So the cos means adjacent side by hypotenuse, R2 divided by Z2, right? The general formula available, R2 divided by Z2, right? So R2 divided by Z2 is nothing but R2 square plus X2 square, general formula under standstill condition. The same thing under the running condition mean we need to add the slip of the induction motor. Same formula only, R2 divided by Z2R. This R refers the running condition. The resistor value is same for both running condition as well as starting condition, right? So Z2R is nothing but R2 square plus S into X2 square, right? So this is a formula for power factor under standstill condition. This is for under running condition. During running condition it is depends upon the slip of the induction motor. So in this video we discuss about the slip of the induction motor, definition and the formula, and effect of the slip on rotor parameters. 5 parameters we discussed. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Thank you for listening.